Hello everybody. Part B of the Experiment Organic Polymer Fun involves examination of household films, both Teflon, and we have a piece of Teflon tape that we use in plumbing, and high-density polyethylene. We have a piece of a grocery bag, which is composed of high-density polyethylene. If you think about it, molecularly, the chains of polymers can be arranged in different ways. If I use my fingers as an illustration, if I have the polymer chains running parallel to each other, it's pretty strong. I'm pulling my hand apart and I can keep my fingers together just like you can keep the polymer strands together. However, if I pull it the other direction, there's nothing to keep the strands together and the material should stretch nicely. Okay? So why don't we try it with the Teflon tape first. Now the Teflon tape, I'll first pull it long ways. I won't overpower it because I am strong enough to break it, but I'll give it a good tug, and I can see not much is happening. Okay? But if I turn it the other way, and I pull it on the short end, I easily stretch it. This should be a clue to you of how the fibers are arranged, the polymers are arranged in Teflon. Now, here's my grocery bag. Okay, a piece of my grocery bag. Now you can see it came from Giant, of course. When you carry a grocery bag, you carry it like this, right? You hold it up like this. So if I first pull it in that direction, and I won't overwhelm my strength, but I can see it doesn't really give much, right? It's pretty stable. But now if I turn it the other way, the way it's not designed to be carried, I give it a little tug. Look how easily it stretches. Pretty cool, huh? Same power, same strength. I'm pulling it. One way it won't budge, the other way it does. If I go back now, and now that I've maybe rearranged the fibers a bit and I pull it this way, look, and now it stretches this direction pretty easily till it breaks. All right. Next will be slime. All right, we'll continue to part C. Now, you will have received kits to make slime, so I won't demonstrate that for you. But we'll talk about the chemistry involved in making slime. We have what's known as polyvinyl alcohol. It is a polymer, an addition polymer, where vinyl acetate groups, will polymerize to form polyvinyl acetate. And the acetate groups will be hydrolytically cleaved in water to form what's known as polyvinyl alcohol, or PVA. You buy this as a white solid. Because it has all of these hydroxyl groups on there, it's very soluble in water. These OH groups can make hydrogen bonds with water molecules, so even though it's a polymer, and most polymers you don't think of being water soluble, polyvinyl alcohol is. Now, polyvinyl alcohol is an interesting substance in that it dissolves in water, but what really becomes interesting is when we make and use a substance called sodium tetraborate, or borax. Here's the chemical structure of a borax molecule. And you can see there are 4 hydroxyl groups. So just like water can form hydrogen bonds with polyvinyl alcohol, the borax can. And then depending on the relative concentration of the borax to the polyvinyl alcohol, it can offer some degree of solidity versus the PVA dissolved in water by itself. The more borax we have, the more gelatinous or more solid it'll be. So think about that as you prepare your samples. You're going to prepare 2 samples of slime, one with a higher concentration of borax than the other. And you'll record your result in your data table.